Hello there. So in this talk, I'll be discussing the problem of L2 gain analysis of coupled linear 2D partial differential equations using linear partial integral inequalities. And in particular, we will be focusing on linear second order PDEs, meaning that we have derivatives of at most second order along both spatial variables. Now, we also assume to have some finite dimensional disturbances W and some finite dimensional regulated output Z. So for example, in optimal control, we may want to minimize the effect of these disturbances on this output Z. And one way to quantify this effect is using the L2 gain, which we define as the ratio of the L2 norm of the outputs over that of the disturbances, taking the supremum over these distributions. Now, in practice, we want to minimize this L2 gain, but in order to do that, of course, we first need to be able to establish a value of this gain, or at least an upper bound on this value. And that will be the focus of this talk. Now, we note that for 1D partial differential equations, we actually already have a framework for computing a bound on this L2 gain, namely using the partial integral equation, or PI representation. In particular, we note that any well-posed linear 1D partial differential equation can be equivalently represented as a PI of this form, where each of these operators A, B, C, D, and T is a partial integral or PI operator, defined by these partial integrals and parameterized by 3 matrix-valued functions. Now, crucially, in this PI representation, the state you had here does not have to satisfy any boundary conditions or continuity constraints, unlike in the PDE representation. And as a result, we can actually compute a bound on the L2 gain for this partial integral equation using the KYP lemma, saying that if there exists a positive semi-definite pi operator P, such that this pi operator Q here is negative semi-definite, then for any bounded disturbance W, the output Z will also be bounded, and the L2 gain of the system will be bounded by gamma. So using this approach, we can compute a bound on the L2 gain of 1D partial differential equations by solving this linear pi inequality, or LPI. Now what we want to do then, of course, is extend this approach to 2D partial differential equations, finding an equivalent representation of such systems as a pi. In particular, we want to find a representation of 2D partial differential equations that is parameterized by pi operators and is free of boundary conditions, such that we can also use the KYP lemma to compute a bound on the L2 gain of such systems. Now, in order to do this, of course, we first need to define what our pi operators actually look like in 2D. So in 2D, we define the partial integral operators using 9 matrix-valued functions, using a multiplier term, these 2 partial integrals along just the x direction, these 2 partial integrals along just the y direction, and then these 4 double integrals along both the x and the y direction. Now we will denote the set of pi operators using this letter capital Pi, and we note that crucially, this set of pi operators actually forms a star algebra. That is, the sum of 2 pi operators is a pi operator, the composition of 2 pi operators is a pi operator, and the adjoint of a pi operator is a pi operator, meaning that we can freely perform these operations on pi operators. So then, having defined a class of partial integral operators in 2D, next, we want to compute an equivalent representation of our 2D PDEs in terms of these pi operators. And in order to do so, we will first look at what our partial differential equation actually looks like in 2D. So we note that any linear second order 2D PDE can be represented by a bunch of matrix-valued functions. So for example, we have these functions aij here, describing the contribution of each allowed derivative of our state u up to second order to the PDE dynamics. Similarly, we have these functions cij here, describing the contribution of these derivatives to the output z. And we have these functions b and d here, describing the contribution of the disturbances to both the PDE dynamics and the output. Finally, we also have this pi operator e here, which we use to describe our boundary conditions in this slightly abstract format. So in this format, we use this full boundary vector, lambda bf, to describe our boundary conditions. And this full boundary vector basically collects a bunch of values of the state as well as derivatives of the state along the boundary of the domain, allowing us to represent a very general class of boundary conditions, as we will discuss in more detail in the next slide. So if we then consider, for example, our reaction diffusion equation, we note that in this system we have these second order derivatives along both the x and y direction, parameterized by cx and cy. So we set a20 and a02 equal to cx and cy. Similarly, this term lambda here involves no derivative of the state, so we set a00 equal to lambda. And since also the output z here involves no derivative of the state, we set c00 equal to 1. Finally, we scale the disturbance in the PDE dynamics with a vector of 1. Now, to describe our Dirichlet boundary conditions here, we describe them in terms of these corner values, as well as these second order derivatives of the state along the lower and upper boundary of the domain. So why do we use this representation for boundary conditions? Well, we want to be able to represent as many boundary conditions as possible in a compact format. But in 2D, the boundary is rather complicated. In particular, we have these corners where the state is finite dimensional, but we also have these edges along the x direction and these edges along the y direction where the state is one-dimensional. So in order to be able to represent as many boundary conditions as possible, we will seek a minimal representation of these boundary conditions. So for example, if we consider the value of the state along the lower boundary of the domain, we note that we can express this value in terms of the value at the lower left and lower right corner, over here and over here, as well as the second order derivative of the state along this lower edge. Now, since our PDE state is only second order differentiable along each spatial direction, we note that this second order derivative of the state cannot be decomposed any further, and we refer to this representation as minimal. So in this way, we can equivalently represent our Dirichlet boundary conditions here in terms of these corner values and this second order derivative, or in terms of this minimal representation. So we will collect these states defining these minimal representations in our full boundary vector, allowing us to represent a variety of boundary conditions, including Dirichlet conditions, Neumann conditions, Robin conditions, so long as these conditions are all homogeneous and not, for example, periodic boundary conditions. So then we've defined our partial differential equation and our boundary conditions. Now, in order to derive the pi representation, we want, of course, to get rid of these boundary conditions, as there are no boundary conditions in the pi representation. So in order to do that, we will use Cauchy's rule for repeated integration, which tells us that basically for any one-dimensional function, we can express it in terms of the value of this function at the lower boundary, and a partial integral of the highest order derivative of this function on the interior of the domain. So for example, in our case, we note that our PDE state here is second order differentiable, so we can express it in terms of this second order derivative of the state along the interior of the domain. Now this is only in 1D. In our case, of course, the function is two-dimensional, so we must generalize Cauchy's rule for repeated integration to 2D. And to this end, we note that each of these states here is still actually a function of y, and moreover, they are all still differentiable with respect to y. So what we can do is we can apply Cauchy's rule for repeated integration to each of these states here along the y direction, yielding this general representation in terms of these corner values, these values along the lower edge, and these values along the left edge of the domain, as well as this second order derivative of the state along both spatial variables on the interior of the domain. Now we note that since our state u here is only second order differentiable with respect to each spatial variable, we cannot decompose this state any further, and in fact this state will be free of any boundary conditions and continuity constraints imposed upon our PDE state. So we will refer to this state as our fundamental state. Now what we want to do then is we want to get rid of these boundary values in this representation so that we may express the PDE state directly in terms of our fundamental state. And to this end, of course, we will impose our boundary conditions. So first, we collect all of these boundary values from the previous slide into this core boundary vector lambda BCU, allowing us to express the PDE state in terms of this core boundary vector and our fundamental state using pi operators k1 and k2 in this compact format. Then we consider our boundary conditions, where we note that since we can express the PDE state at any point in our domain in terms of these core boundary values and our fundamental state, we can also express the boundary values at the value of the state at the boundary of the domain in terms of these core boundary values and this fundamental state using pi operators h1 and h2. Then, of course, we can invoke our boundary conditions, where we substitute our expression for the full boundary vector into our boundary conditions, yielding this expression for our boundary conditions. Then we can move our core boundary state to the other side of the equation to find that we can express the core boundary state in terms of our fundamental state, assuming this operator EH1 here to be invertible. Finally, we can substitute this expression into that for our partial differential equation state to find that we can represent the PDE state in terms of this fundamental state directly using a pi operator t. And this is really the crucial result at the basis of this entire methodology, namely that for a given operator E such that the boundary conditions are well posed, that is, that this operator EH1 is invertible, there exists a pi operator t such that for any state u, we can define an associated state u equal to t u hat, such that this state will satisfy our boundary conditions. Now, substituting this relation between the PDE state and the fundamental state into our partial differential equation, we obtain an equivalent representation of the system as a partial integral equation, where we note that each of these operators a, b, c, d is a partial integral operator defined by taking the composition of this differential operator with our pi operator t. Now these two representations are equivalent, meaning that for any solution u hat to the system to the pi, we have a solution u to the PDE, and for any solution u to the PDE, we have a solution u hat to the pi. Moreover, in this representation, the pi representation, the state u hat does not have to satisfy any boundary conditions, meaning that we can compute a bound on the L2 gain of the system using the KYP lemma. In particular, for a partial integral equation of this form, we note that we can parameterize a quadratic storage function by a pi operator p, and then the derivative of this storage function along solutions to the system must satisfy this identity here, where q will be a pi operator as well. Then we can prove the KYP lemma, namely, if there exists a positive semi-definite pi operator p such that this operator q here is negative semi-definite, then the L2 gain of our partial integral equation will be bounded by gamma. Now here we can parameterize a set or a cone of positive pi operators using positive matrices, saying that for a given pi operator z, p is an element of this cone if we can decompose it in this quadratic format here. And then if p is an element of this cone, that guarantees that p is in fact a positive semi-definite operator, meaning that we can parameterize positive semi-definite pi operators by positive semi-definite matrices, and thus we can solve this linear pi inequality using semi-definite programming. Now here we will choose these pi operators z here to be parameterized by monomials of a particular degree d. And then unfortunately, the size of these monomials will increase with d squared, meaning that the complexity of our semi-definite program will increase with d to the power of 4. So that's a challenge that we have to work on. Now we've incorporated this entire approach into the MATLAB toolbox PIETOOLS, allowing us to test a bound on the L2 gain in 3 steps. In particular, first we declare the PDE as a PDE structure. Then we convert the PDE to an equivalent partial integral equation by simply calling convert. And then we solve the L2 gain LPI by calling the appropriate executive function, returning a value of gamma that is an upper bound on the L2 gain of our system. Now, using this approach, we tested the L2 gain, or a bound on the L2 gain, for our reaction diffusion equation for various values of our reaction parameter lambda, where we note that this system is stable if and only if lambda is smaller than 2 pi squared. And indeed, as lambda approaches the value of 2 pi squared, this bound on the L2 gain grows to infinity. Now, for comparison, we also computed a bound using discretization, or more accurately, we computed an estimate. So we discretized this system using a central finite difference scheme on a 12 by 12 grid. And then we computed an estimate of the L2 gain by solving the KYP lemma for this discretized system. And we find that for each value of lambda, the obtained bound on the L2 gain using the LPI approach is smaller than the estimated value using discretization. Now, for our additional tests, we considered some variations on our reaction diffusion equation, such as distributed reaction term, distributed disturbances, or replacing these upper Dirichlet conditions with Neumann conditions. And we find that for each of these 3 tests here, the L2 gain bound that we obtained using the LPI approach is smaller than the L2 gain estimate using discretization. And the computation times in general are also smaller, even though they are still quite large. So with that, we've reached a conclusion. The main takeaway would be that using this approach, we can compute a bound on the L2 gain of a linear 2D partial differential equation using semi-definite programming. And in particular, we extended the framework for 1D pies to 2D. So in general, this framework is very similar between the 1D and 2D case. The main challenges are with the boundary conditions, as well as the computational complexity of the LPIs, which increases with the monomial degrees to the power of 4 in 2D, whereas it increases with the monomial degrees squared in 1D. So that's a challenge we've yet to work on. And with that, I would like to thank you very much for your attention.